My name is Regan Ford. I'm a geography educator at Belgravia High School, and I will be doing climatology, climate, and weather with you this afternoon. As you can appreciate, the volume of work that we have to cover is quite a bit, and we only have an hour in which to do it. So I will select items that we will look at, and I will go through it with you. Firstly, I have to thank Mr. Glenn Samai for providing us with the material that I will be using this afternoon in my lesson. We start off with mid-latitude cyclones. And in the mid-latitude cyclone section, we will be briefly looking at cold and warm fronts, characteristics of mid-latitude cyclones, the stages of a mid-latitude cyclone, and the weather associated with a mid-latitude cyclone. Now, very important, what are warm and cold fronts? Learners get confused with the term warm and cold front, and instead of describing a warm front or a cold front in the exam, they describe the air mass, the warm air mass or the cold air mass. So what is very, very important to note is that if you look at the slide, with a warm front, we have, the warm front is on this side, we have warm air behind cold air. If I look at the cross section over here, the warm air mass is behind the cold air mass. This is the front of the warm air mass, where your warm air is moving in behind the cold air, and therefore it is the warm front. Here we are looking at a cross section through a warm front, as you would see it on the surface of the earth, and here we are looking at a warm front as it would appear on a map. Notice the temperatures here, 26, 28 degrees Celsius, and on this side, 17 degrees, 19 degrees Celsius. So the air ahead of the warm front is cold, the air behind the warm front is warm. Let's look at the cold front. Here we have a cross section through a cold front. Cold air behind it. This is the front of the cold air mass. That's the rear of the warm air mass. The cold air is pushing in behind the warm air, so that is the cold front. This is how we see the cold front on a map. Once again, notice cold air, this is the front of the cold air mass, 14, 16, 18 degrees Celsius, and this is the rear of the warm air mass, 27, 24, 28 degrees Celsius. So learners, it is very important that you know the definition of a warm and a cold front, and that you can identify it, and that you can explain, what it is. We're now going to move on to the characteristics of a mid-latitude cyclone. And on your screen, you have a sketch, as it would appear on the map, of a mid-latitude cyclone. You will immediately be able to recognize certain elements of your mid-latitude cyclone. For example, your low-pressure center in the center here. There's the cold front. There's the warm front. And this show me, just by looking at those three elements, I can see that this is indeed a mid-latitude cyclone. Isobar. What is an isobar? Anybody? Nothing on the screen, no questions yet. An isobar is a line joining places of equal atmospheric pressure. And we can see, for example, here that this isobar has a value of 1,000 hectopascals, or millibars. Those are the units that we use to measure atmospheric pressure. There's an isobar of 996, 992, and that tells me that the isobaric interval is 4 hectopascals, because there's a gap of 4 hectopascals between each isobar. How do I know it's a low pressure cell? The value of the isobars is decreasing as I move to the center. There's my low pressure center. My cold front that we've already identified. The warm front that we've already identified. Look at the circulation of air. In which direction is the air circulating? In a clockwise direction. What does that tell me? What do we have to know about the direction of circulation? We know that a cyclone or low pressure cell in the southern hemisphere has a clockwise circulation of air. See the circulation in a clockwise direction, and this tells me that this cyclone is in the southern hemisphere. The warm sector and the cold sector. The air here is warm. We call it the warm sector. And the air right around here is cold. We call it the cold sector. Let's have a quick look at those fronts again. Same fronts. This is the front of the warm air mass, of the cold air mass as it's pushing in behind the warm air mass. This is the front of the warm air mass as it's pushing in behind the cold air mass, and hence the warm front and the cold front. The development of a mid-latitude cyclone. Now, this is very, very important because you have to know the stages. In your exam, you can be asked, you can be given a sketch. I'll show you one or two now. You can be given a sketch of a mid-latitude cyclone, and you can be asked in which stage of development is this particular mid-latitude cyclone, and then you're going to have to explain why you chose that particular stage. So let's look at the slide. The initial stage. Here, we know from your class, from your lessons in class, you know that you have warm air here coming from the subtropical high pressure cell, moving from west to east. And you have cold air coming from your polar regions, from the polar high pressure cell, moving from east to west. And these two air masses initially move past each other along a boundary called the polar front. Along a boundary called the polar front. So, the next step. A wave develops along my polar front. And this wave creates an area of low pressure here. Now, why does this area of low pressure develop here? Very, very simple. Because this area where I'm pointing to now used to be occupied by cold air. And can you see how the warm air here has pushed into an area that used to be occupied by cold air? And we know that when the temperature goes up, when the air becomes warmer, the pressure will drop, the atmospheric pressure will drop, and a low pressure center develops here. Air starts to circulate, and that's the development stage. We now have the mature stage. See, there's my polar front. But along my polar front, I can identify certain new characteristics. I can see, for example, that there's my cold front, cold air pushing in behind warm air. There's my warm front. But this is still that same polar front that we have over there and that we have over there. The only difference is that my cold front moves much faster than my warm front, so it's busy catching up. And when my cyclone has this distinct V shape, where I can differentiate between a cold front component and a warm front component, and I can see a definite warm sector, I now know that my mid-latitude cyclone is in the mature stage. The last stage is known as the occlusion stage. What does that mean? That means that my cold front has eventually caught up with my warm front. Look at this here. Can you see? If I look over there, there's a distinct cold front, there's a distinct warm front. But this part here, can you see that the cold front and the warm front have merged? They've become one. The cold front has actually caught up with the warm front. And here it has not. And it will catch up and catch up. This part here is going to close almost like when you're pulling up a zip. When you have a zipper on your jacket and you're pulling up the zipper from the bottom, the zip closes from the bottom up, and I want you to picture that. So this will close, and we say that this part here has already occluded. The cold front has caught up with the warm front, and here I still have cold front and I still have warm front that still has to catch up. And this warm air here, as the cold front catches up with the warm front, this warm air will be lifted up into the air and until I have only cold air on the Earth's surface. Now, let's look here. Here I have how many mid-latitude cyclones can you identify? Here, I'm looking on the screen and I see that somebody says 3, and that's absolutely correct. There's one. There's no L there, but this is the low pressure center. There's a mid-latitude cyclone. There's one, and here's my third one. And when we have so many mid-latitude cyclones, 2 or more mid-latitude cyclones that are linked, we say that is a family. We call it a family of fronts. Now, can you see that front is in the development stage? Look at it. The cold front is there, the warm front is there, but it is not open wide. I can't see a definite warm sector yet. That one over there is in the mature stage. And the third one is in the occlusion stage. Now, while we have the sketch open, of these three, let's call this one number 1, let's call that one number 2, and let's call this one number 3. Which one do you think is the oldest? Which one was formed first? Let's see if I can get any answers. I'm waiting for some answers on the screen here. Remember what I said, that's number 1, that's number 2, that's number 3, and quite a few people are saying that number 3 is the oldest, and they're absolutely correct. The reason for that is we know that mid-latitude cyclones move from west in an easterly direction. This one is the furthest to the east, and therefore it will be the oldest because it has traveled the furthest. Also, it is in the occlusion stage already. This one is still developing. So there are 2 reasons that I can give why this one over here is the oldest mid-latitude cyclone. It's found the furthest to the east of the 3, and it is already in the occlusion stage, whereas this one is in the mature stage, and that one is in the development stage. Let's move on. Family of cyclones we spoke about. Let's look at the typical exam question. Write a paragraph in which you explain the development of an occlusion. Let's have a look at how the occlusion develops. Here I have the mature stage. There I have the occlusion stage. By now you know already, mature stage, there's a definite cold front, there's a definite warm front, and there's a definite cold front, there's a definite warm front, and there's a definite warm sector. Whereas in the occlusion stage, the cold front has started to catch up with the warm front. Now, when you have to write a paragraph, remember you only need 4 to 5 points. You get 2 marks. Your paragraphs are never more than 8 marks. Write a paragraph in which you explain the development of the occlusion. Here's your answer. The air behind the cold front is cold. So in other words, this air here is cold. The cold air moves faster than the warm air, so the cold front catches up with the warm front, right? So this cold front will close this gap here, and there we can see it's starting to catch up already. The cold front undercuts the warm front, and the warm sector is lifted off the surface. Now let's have a look at the sketch here. Can you see the cold front? There's my line separating the cold air from the warm air. That's my warm front. But can you see what has happened along the Earth's surface? I have cold air and cold air. So this here is a section through this part here, where the warm air has been lifted up. There's cold air. This cold air here that I'm showing you now is this cold air here. The cold air here, ahead of the front, is that cold air. Where's the warm air? It's up here. You can't see it because here we're looking at it from the top. But here we can see the warm air because we're looking at it from the side. Now, this type of occlusion is called a cold front occlusion because my cold front remains on the ground. The cold air behind the cold front is colder than the cold air ahead of the warm front. So my cold front remains on the ground, and the air here ahead of the warm front is lifted up, which makes this a cold front occlusion. If it had been a warm front occlusion, then that line would have continued to the ground, and this line would have ended there. That would have been a warm front occlusion. Describe the weather changes associated with the passing of a warm or a cold front. Now, before we look at this slide, learners, for you learners living in the Western Cape, this should not be a problem, especially the cold front. Why? Because we know what cold front conditions are. When it's winter, you watch the weather on television in the morning, and your mother will tell you, you need to take a jacket, you need to take an umbrella. Why? Because we know that when cold fronts are approaching, certain things are going to happen to the weather. The weather is going to behave in a specific way. And we're going to look now at the slide to see what exactly will happen. Firstly, when a warm front passes, we very seldomly feel warm fronts over Cape Town, but more especially when a cold front passes. So let's have a look at the slide. So I have a mid-latitude cyclone. Once again, you can see it's the mature stage. What do you see on the weather stations? Let's look at the temperature. Where do I find the temperature on the weather station? It's the top number. 18 degrees Celsius is the air temperature here. Look at the temperature there, 24. Why is there such a big difference? 16, which tells me that this here is the cold sector. That's my cold air. There's the warm sector, my warm air. I can already tell that when this mid-latitude cyclone, when this particular mid-latitude cyclone reaches the occlusion stage, it will be a cold front occlusion and not a warm front occlusion. How do I know that? I look at where the air is colder. 16, 18. This air is colder, it's going to remain on the ground. This air of the two cold air masses is warmer. This is the one that's going to lift up. So this is going to be a cold front occlusion when it occludes because the temperature there is lower. Now, what are the weather conditions that are associated? When the warm front passes, remember that's the warm front. So if you're standing here, and remember your system is moving in that direction. So if you're standing over here and the warm front passes over you, the temperature is going to rise. Look, it's 18 there. When the warm front passes over, it's going to be 24, so the temperature is going to rise. The atmospheric pressure is going to drop. If I'm standing here, the atmospheric pressure is 1,008, and as this thing passes over me, it's going to drop to 1,006 and even lower. The wind direction is going to change from northeast. See, this wind is blowing from the northeast, and when this part of the mid-latitude cyclone is over me, the wind will be coming from the northwest. The cloud cover is going to decrease. Notice here, 75% cloud cover, 25% cloud cover, and the rainfall will stop. It will rain initially as the warm front passes over, but then the rainfall will stop. When the cold front passes over, let's have a look. The temperature is going to drop. Let's see. If I'm here, the temperature will be 24, and once the cold front passes, what's it going to be? 16. Temperature will drop. The atmospheric pressure is going to increase. Let's look at the wind direction. Here it's coming from the northwest, as we said earlier. You see there? And what's it coming from now? From the southwest. And this change of wind direction, first from that side, northeast, then from northwest, then from southwest. My wind direction is changing in an anti-clockwise direction, and we are saying that the wind backs, or the wind is backing. Cloud cover is going to increase. Notice there, 100% cloud cover, completely overcast, and that leads to heavy rainfall. Grade 12 learners, you need to know the conditions that's going to occur when a warm front passes over you and when a cold front passes over you. That's a question, a typical exam question that comes in almost every year. Please make sure that you know it. You will get between 4 and 8 marks, depending on what is asked. You will get between 4 and 8 marks for that particular question. So please make sure that you know it. And now I have another animation for you that's going to show you the changes. So just bear with me. It takes a little bit of time. There's a young man walking, or a young lady, not very gender specific. And you see the warm front approaching. It rains, you see the nimbus stratus clouds, you can see the cold air, you can see the warm air, the front of the warm air pushing, and the warm front has passed. Notice the clouds have disappeared, the rain has stopped, and this person is now in the warm sector. Cold front approaches rapidly. When the cold front comes over, there's our cumulonimbus clouds, extremely heavy rainfall, little bit of respite followed by cumulus clouds with a little bit of more rainfall. The temperatures dropped, it has become much colder, and this person is now experiencing typical cold front conditions where the cloud covers 100%, lots of rainfall, lower temperatures, atmospheric pressures drop, the wind has backed. And that basically covers mid-latitude cyclones. If you go through the sections that I've spoken about now and you become comfortable with it and you know everything, you should be able to answer any question on mid-latitude cyclones that is thrown at you. Next, if you look at the next slide, we will see that we will quickly go through tropical cyclones. And here, there's a little bit more. We will be looking at the favorable conditions for tropical cyclones to occur, the characteristics of tropical cyclones, the location, in other words, where do we find tropical cyclones, the weather patterns associated with tropical cyclones, the stages, and how to manage tropical cyclones. So, let's have a look at our first slide. The characteristics of tropical cyclones. I'm not going to explain them to you. Your teacher would have taught it to you and you should have studied it, but I will just go quickly through the characteristics and show you what you need to know in order to be able to answer exam questions. So, tropical cyclones. Firstly, where do they occur? We know that they occur within the tropics, in other words, between 23.5 degrees north and 23.5 degrees south of the equator. We know that they form over the oceans, over the tropical oceans of the world. And we also know that they do not occur within 5 degrees of the equator. The reason for that, Coriolis force does not occur within 5 degrees of the equator. And you know from what your teacher has taught you that one of the requirements for a tropical cyclone to occur is that Coriolis force must be present. So between 23.5 degrees north and 23.5 degrees south, we will find tropical cyclones forming, but not within that band, 5 degrees north and 5 degrees south of the equator, very simply because there's one element that's missing, and that is Coriolis force. Within 5 degrees of the equator, the temperature is high enough, it's well over 27 degrees Celsius, the ocean temperature, there's enough humidity, there's enough convection, all the elements are there, but that one element, that Coriolis force, has to be present. That element is missing, so we don't find them forming within 5 degrees of the equator. Let's go back to our slide quickly. So, tropical cyclones are moving in an opposite direction. The tropical easterly winds are carrying, so they move from east to west. And we see that east to west movement here. Notice, curving away from the equator. Coriolis force is causing it to curve away from the equator. Tropical cyclone is progressing away from the equator. You should know by now that the center of the tropical cyclone we call the eye, and the characteristics of the eye, there's no wind, no rain, no clouds. 3 characteristics. In the exams, refrain from saying that it is calm. You'll get 2 marks for saying that. The eye is calm, which is the truth. But if you say there's no rain, describe that calm. No rainfall, no wind, no clouds. You can get up to 6 marks, once again, depending on the question that is being asked. Let's move back to our slide. And our tropical cyclone hits Madagascar. This tropical cyclone has formed over the southern Indian Ocean. It's moved from east to west. It's curving away from the equator, following a rather erratic path. And it hits poor old Madagascar. We get hit by tropical cyclones often. And what happens? The tropical cyclone starts to slow down. Why does the tropical cyclone slow down when it moves over land? And sometimes it completely dissipates. 2 main reasons why. When a tropical cyclone moves over land, it loses its source of moisture. It's not over the ocean any longer. So all that moisture that has been evaporating, that source of moisture is lost. And we know that the source of moisture, the water vapor coming up from the ocean, condenses, gives off latent heat, and this latent heat is the energy that powers my tropical cyclone. So when the tropical cyclone moves over land, it loses that source of energy. And also the friction. The tropical cyclone, when it's moving over the ocean, it's a nice smooth surface, and it sails along nice and smoothly. The minute it comes to land, there's much more friction. There are buildings, there are trees, there are mountains and rocks and things in the way, and all that friction slows the tropical cyclone down, which eventually causes it to dissipate. So let's go back to our slide. It has moved over Madagascar and over Mozambique, and notice the destruction. Typical exam question, very, very popular question. This question could also be in the form of an essay. Describe what happens to coastal areas when a tropical cyclone strikes. The destruction. When you are giving your answer, refer to 3 things. Refer to the winds and say what the destruction is. Refer to the torrential rain, the extremely heavy rainfall, and refer to the flooding. Those are the 3 things that you need to refer to. You can then elaborate. What would the wind do? The winds would uproot trees. The winds could destroy crops. Winds could destroy property, infrastructure, things like traffic lights, etc., power lines. So those are all things that the winds can destroy. So the wind is the point that you can refer to, but then you can go on and explain the chaos and the devastation caused by the wind. You can then refer to the torrential rainfall, explain how the rainfall can reduce visibility, how it can increase motor vehicle accidents, how it will affect ships at sea, how the heavy rainfall will cause flooding, etc., etc. And then you can go on to the flooding and expound on what the damage caused by the flooding. Once again, crops being washed away, infrastructure being destroyed, buildings being destroyed, etc. So That is how you're going to answer a question. But remember, you must just remember the three things: the storm winds, the torrential rain, and the flooding. And once you remember that, you can then use your own knowledge to expand on that. Let's go back to the slide, and we see that the tropical cyclone, once it reaches about 30 degrees, in this case south of the equator, obviously one in the northern hemisphere, when it reaches 30 degrees north of the equator, will then start to turn east and move back to sea. Once again, we see that when it moves over land, it dissipates. And just to recap, no moisture, no more warm air, which is the source of energy for the tropical cyclone, and the friction between the tropical cyclone and the land, which causes it to slow down. Now, learners, on this slide, on that slide that you just looked, we'll go back to it in a moment, but on that slide that you just looked at now, most of what you need to know about tropical cyclones appears there. And it looks quite simple now, doesn't it? It looks quite simple. Where does it occur? Characteristics of the eye. In which direction does it move? Why does it move in that direction? What's the destruction that it causes when it moves over land? Where does it turn east? And why does it dissipate when it moves over land? That, I would estimate, is up to 80% of the questions that could be asked on tropical cyclones. So please ensure that you know it. Obviously, what you also need to know, it's not on the slide, I'm not going to go through it now with you, but that list that your teacher did with you, what requirements are necessary for a tropical cyclone to form. The fact that the sea temperature, and learners, it is the sea temperature, not the temperature of the air. The ocean temperature has to be 27 degrees Celsius or higher. There's got to be high humidity, convection, strong convection, etc., etc. That list you need to know. Now, something that's been coming up in the last 2 years. The exams in the last 2 years have been focusing on super typhoons, super tropical cyclones, where your tropical cyclones are more intense than usual. And when you are asked, just listen to me very carefully now, when you are asked, what are the requirements for a super tropical cyclone or a super hurricane or super typhoon to form? Use that same list that your teacher did with you, but exaggerate everything. The temperature has to be much higher than 27 degrees. There's got to be extremely high uplift of air. The humidity's got to be extremely high, very, very high. So you use exactly that same list of requirements for a tropical cyclone, but you exaggerate it when you are asked, why is there a super hurricane or a super typhoon? Let's look at an exam question now. Here's a few questions. Some of the answers are on the screen already, and the others we will discuss. So here's a cross-section through a tropical cyclone. A typical tropical cyclone, here's a cross-section through it. And I can see there's the eye. Here's air busy rising within the eye. There are my spiraling winds, water vapor coming in from the sea. The first question was, give evidence to prove that this is in the northern hemisphere. And once again, the answer's there already. It is the anti-clockwise. This is a cyclone. And the minute a cyclone moves in an anti-clockwise direction, it has to be in the northern hemisphere. If this had been in the southern hemisphere, then the rotation of air would have been that way. Why is the descending air in the eye dry? This air that's moving down the center, it says the descending dry air. Why is it dry? Because when air sinks, it becomes compressed. It can't condense. Sinking air becomes compressed and warms up. Air cannot condense when it's becoming warmer. Air condenses when it is cooling down. So rising air, the air on the outside that is rising on the outside of the eye wall, that air is giving off moisture. It's condensing and giving off moisture. But the air that's sinking in the middle is warming up so it doesn't condense. Name the section of the moving cyclone where the highest wind speeds are recorded. Now, we know, I'm just going to draw something for you quickly. We know that a cyclone, let me just draw, let's just say this is going to be 980 hectopascals here. — 89, 69, 40. Sorry for my very, very ugly handwriting. But we know that the circulation of air within a cyclone, I'll do one in the southern hemisphere, that we have a clockwise circulation of air. We also know that the entire system is moving in that direction. that the entire system is moving from east to west. Now, if I divide my tropical cyclone into 4 quadrants, you will notice in this quadrant, my A is moving in that direction, whereas my whole system is moving in that direction. This is like someone on a treadmill. When you're on a treadmill, the treadmill is moving in this direction, but you're walking in that way, so you're really going nowhere. You're standing on one place. But if I look at this quadrant here, this is the only quarter or quadrant where my A movement, my direction of rotation, and the direction of movement is in the same direction. So this is like you being on a treadmill but going in the wrong direction. The treadmill is carrying you that way and you're running that way. So in other words, in this quadrant here, my wind speeds are going to be the highest. Why? Because my direction of rotation of my EMS and my direction of movement of the entire system is the only of the 4 quadrants. It's the only one where they are going in the same direction. And this quadrant here, in this case, watch here, this is left, that's right, this is the front, that's the back. So this quadrant is my leading left-hand quadrant, also known as the dangerous semicircle. It's also called the dangerous semicircle because in that quadrant, the highest wind speeds will be recorded. So to answer this question, number 3, the section of the moving cyclone in which the highest wind speeds are recorded is my leading left-hand quadrant in the southern hemisphere. In the northern hemisphere, it will be the leading right-hand quadrant, also known as the dangerous semicircle. The next question, explain why satellite images are effective for tracking cyclones. And I'll answer that question now. And the last question, write a paragraph to outline the economic and environmental impact of tropical cyclones. I'll come back to that question also. So let's look. Here we have the northern hemisphere. Remember what I showed you earlier? In this case, it is going to be the leading right-hand quadrant. Why? Because here, that's the direction of movement, and my cyclone is moving in that direction. So this quadrant here, the leading right-hand quadrant, will be my dangerous semicircle where my winds are blowing in the same direction that the cyclone is moving. My dangerous semicircle. Wind direction, same direction as which the storm is moving. The next question, why are satellite images effective? Very, very simple. Your data is received in real time. The satellite is transmitting data constantly. So you can see at any particular time, if I look at this satellite image in front of me, I see numbers 1, 2, 3, 4, 5, showing the location of this particular tropical cyclone at a particular time as it is moving towards the Gulf of Mexico. You can see here's the Gulf of Mexico. This is my east coast of the USA. New York would be along this coastline here. Here's the northern part of South America and my tropical cyclone moving in that direction. We can monitor the data every hour or even every 30 minutes should we decide to do so. We can determine the intensity of the storm. Look at here, I can see that when it was at this stage, I can see the size of my cloud cover, and look at the size of my cloud cover here. Here the storm is much more intense. I can predict the path. When it was at this stage, I could have predicted that it's going to move more or less in that direction. And we can monitor large inaccessible areas. If the area is over the ocean or in a mountainous area where it's difficult to get to monitor, by using the satellite out in space, can track. And that is the answer to the question why satellite images are effective for tracking cyclones. The other question I want to come back to quickly. Sorry about that. Question 5, write a paragraph to outline the economic and environmental impact. Now, I'm not going to go into too much detail here, but when you get a question like that, question is twofold. Write a paragraph to outline the economic and environmental impact. Now, grade 12 learners, the biggest problem that I pick up at the end of the year when we're busy marking your scripts is that learners don't take the time to read their questions properly. You've got 3 hours. 3 hours to answer 3 questions of 75 marks each. You're going to take about 10 to 15 minutes to decide which of the 4 questions you're going to answer, which then gives you about 55 minutes to answer a 75-mark question, which is more than enough time. So take your time and read the question properly. And if you read, if we could just cut back to that slide quickly. If you read question number 5, write a paragraph to outline the economic, and you notice I highlighted it in red, and environmental impact of a tropical cyclone. So you need to give 2. Now remember, your essay is worth 8 marks. 4 times 2, 8 marks. So in other words, the person that's marking your script, if you're only going to look at the environmental impacts or only at the economic impact, they're going to give you a maximum of 6. 3 times 2, 6. Why? Because you didn't answer the other part of the question. You need to outline the economic and environmental. So in other words, you could give 2 economic, 2 environmental. You could give 1 economic, 3 environmental. But if you were to give 4 facts for only economic or 4 facts for only environmental, whoever's marking your script has strict instructions only then to award 6 marks, 3 times 2, because you did not speak about the other element. When it comes to economic, you're going to look at things like agriculture, industries, anything, any economic activities that human beings are involved in. You can speak about agriculture being disrupted, crops being washed away, farmers losing money, the country not being able to produce food, factories, industries having to close down because the electricity supply is being disrupted, the water supply is being disrupted, etc. So those are all things that you can look at when you're answering the economic part of the question. Environmental impact, as the question said, you're looking at the environment. You're looking at the natural vegetation being destroyed. You're looking at, stay away from crops when you're speaking about environmental, because crops would be more economic. You're looking with environmental, you're looking at what's happening along the coast, flooding, the storm surges, etc., 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 and how that impacts on the environment. Okay, I'm not going to give you an answer. You can go and work that answer out on your own, but I think I've given you some guidance as to how to go about answering that question. We're now going to move off from tropical cyclones, and we are going to look now at South Africa's weather. The subtropical anticyclones, the factors influencing the climate of South Africa. We're going to look quickly at line thunderstorms and then also at the South African bergwind. So let's get straight into the factors that influence South Africa's climate. The first factor is the escarpment. Now, you know from grade 8 already, you started in grade 8 looking at this range of mountains here called the escarpment. And we know that if I'm coming from the east and I go up the escarpment, it takes me up onto the plateau, this high-lying area central to South Africa. Let's look first at the influence of the oceans. We know that an ocean can moderate temperatures. Places that are close to the ocean will have cooler summers, warmer winters than places that are further away. But also that ocean currents, we know the story, you've been doing this since grade 10 already, the warm Mozambique and the Gullis current bringing warm conditions to the east coast of South Africa, the cold Benguela current coming here from this polar region, bringing cold, dry conditions to our west coast. So the ocean plays a major role in South Africa's climate. Warm and wet, cold and dry. Then the three anticyclones or high pressure cells. You know that an anticyclone is just another word for a high pressure cell. The South Atlantic and the South Indian that are there throughout the year. Their location varies, they change position. But the South Atlantic and the South Indian high pressure cells are there constantly, and we know, you need to know how the South Indian high pressure cell influences South Africa's weather, and you need to know how the South Atlantic high pressure cell influences South Africa's weather. Then the Kalahari high pressure cell, which is present during the winter months, how it influences South Africa's weather. Then the effect of the plateau, because you're higher up, you're further away from the sea. Because you're higher up, the temperature is going to be lower. We know that an increase in altitude leads to a decrease in temperature. And it will be dry because it is so far from the ocean. Line thunderstorms. Now, what do we need to know here? We know that we have 2 high pressure cells, the South Atlantic and the South Indian. I know that the circulation of air around the South Atlantic will be anti-clockwise. Remember, it's an anticyclone, a high pressure cell. So now we have an anti-clockwise movement. And watch, as this air moves around, it collects cold, dry air from the polar regions, and it feeds that cold, dry air over southern Africa, cold, dry air coming around here and being fed. You can see the direction of movement of the air there over South Africa. And at the same time, we've got warm, moist air circulating, coming here from the tropical regions, and this warm, moist air being fed over South Africa from the northeast. Cold, dry coming in from the southwest, or moist air coming in from the northeast. See that? My warm, moist air, my cold, dry air, you can see it. And where these two air masses meet here, what's going to happen? You know it. When we looked at mid-latitude cyclones, we're going to have a front. There's the cold air mass, there's the warm air mass. A front is going to develop. And this front we call the moisture front. The moisture front, it's a trough. Can you see the shape? It's a trough of low pressure. It's a trough of low pressure that forms where this cold air mass and this warm air mass make contact where they meet. Along the moisture front, we're going to have thunderstorms developing. And because these thunderstorms, why are the thunderstorms going to develop first of all? Because this cold, dry air here is going to remain on the ground. And this warm, moist air, as it comes into contact, it can't push the cold, dry. The cold, dry is too heavy. It can't be moved out of the way. So this warm, moist air rises up over the cold, dry air. And as it rises, it condenses. Clouds form, cumulonimbus form. Clouds form all along this line here. And that leads to the development of line thunderstorms along the moisture front. Let's look at our line thunderstorm very, very quickly. On a synoptic weather map, can you see your cold air moving in, your warm air moving in, and there is my low pressure trough along which the line thunderstorms will develop. Very quickly, why do my thunderstorms occur on the eastern side of this low pressure trough? Because that is where the warm, moist air is coming from. And the last thing we're going to do quickly, the berg wind of South Africa. Notice high pressure over the interior during summer, a low pressure at the coast, either coastal low or a cold front. Air circulates in an anti-clockwise direction. It moves down the escarpment. It is compressed and heated, and it reaches the coast as a warm, dry wind. It reaches the coast as a warm, dry wind. You obviously have to know the conditions that go along with this, that there's the risk of veld fires, that there's uncomfortable warm, dry conditions, and that's all that you have to know about the berg wind. Grade 12s, we do not have time, and your berg wind is obviously followed by a cold front. Now, grade 12s, as I was saying, we don't have time to go through valley climates today, katabatic winds, your city climates. Those things you will have to go through on your own or with your teacher. Urban climates, the heat island effect. I'm just quickly running through things that you still have to know. But those are things that you have to go through on your own, your synoptic weather maps, weather station models, etc. And you will find that if you go through these basics, you'll be able to answer a question, any question in climatology, how to interpret a satellite image. You'll be able to answer any question in climatology, and you will then be successful in your final exam. I hope that the session this afternoon was useful to you. So I'm just going to look at the questions on the screen, and then I have about 8 to 9 minutes left with you, and I will then answer questions. I'm not going to specifically go through those sections with you, but based on valley climates and urban climates, I will just have a look at the questions that are on the screen, and then I will respond to those questions instead of just rushing through things that I think you need to know. Right. Here's a question here. Why do thunderstorms form along the moisture front? Thunderstorms form along the moisture front because at the moisture front you have your cold air, you have the warm air coming, and the warm air is forced up. And as the warm air rises up the cold air, it condenses, clouds form, and it rains. Okay? Let's look if there's another question quickly. More specifically, I'm looking for questions related to valley climates and city climates. Okay. So, when it comes to valley climates, what's the most important things that you need to know? Let's look at the slide. Katabatic and anabatic winds. At night, it is cold. Your cold air slides down the valley slopes. It collects at the bottom. it forms a frost pocket. The question that I looked at on the screen was, can you please explain how a frost pocket forms and how an inversion forms? So at night, air becomes cold. Cold is heavy. It slides down the valley slope. That cold is sliding down the valley slope is my wind that is blowing at night, called a katabatic wind. Katabatic wind flows to the bottom. The cold air collects at the bottom and frost will form. And the frost that forms at the bottom of the valley, we call a frost pocket. The warm air that was at the bottom is now pushed. It is displaced. It is pushed upwards. And colder air coming from the upper atmosphere pushes down, creating an inversion layer. Now, a very, very common exam question is where you will locate your farmhouse, where you will plant various crops along the slope, Obviously, crops that can resist frost, I'm going to plant them at the bottom here. My crops that are sensitive to frost, that cannot take the warm conditions, I'm going to plant them here. Why? During the day, the sun will be shining on them. See, the sunlight will come into the valley during the day and shine on them. And at night, this is where the warmer air is found. So during the day and at night, these crops here will be exposed to warmer conditions and they will be very, very happy there. This is also where I'm going to build my farmhouse. I'm not going to build a house at the bottom here. Why not? It's going to become extremely cold at night. And also, if the river here at the bottom of the valley floods, my house is going to be full of water all the time. So halfway up the slope, I'm going to build it. I'm going to build it on the slope in the southern hemisphere facing north, because that's the slope that's going to be receiving sunlight, and because where it's going to be where I'm going to have my warmer air at night. Then, explain all that to you. Let's look at an exam question. Name wind 1. This is a wind that is blowing up the slope. So it is not a katabatic wind. This is my anabatic wind. This is the one blowing during the day. I can see the sun is present in the picture. That's what you look out for. It is moving up, so that's my anabatic wind. This wind here, number 2, is my katabatic wind. How do I know it's a katabatic wind? It's going down the slope, and the picture shows me that it is nighttime. One difference between winds 1 and 2, I can give you 2. Can you see it's blowing up slope, blowing down slope? During the day, during the night. Warmer wind, colder wind. Okay? There I gave you 3 differences. Would wind 1 or wind 2 originate if a higher pressure occurred at the top of the valley? Now we know that the wind blows from a high pressure to a low pressure. So if the higher pressure is at the top, it would be this one here, because it's blowing from the high to the low. In this case, my higher pressure is at the bottom, because the wind blows from a high to a low. So B is the answer. The wind blows from a high to a low. So here, the higher pressure is at the top. Anabatic, katabatic winds. See that? Everybody happy? Let's move on. Explain why visibility on the valley floor at 3 is less on winter mornings. Draw a label diagram to support your answer. Now, the learners often we see draw a label diagram and we start to panic. There's my diagram. What's happening? Air sinking. I drew in 2 arrows. I drew in an arrow and I drew in an arrow to show air sinking. Why is the visibility? Because the cold air sinking, it's trapping all that smoke, all that smog from the industries, from the cars, engines, etc., from fires that are being made, is trapped at the bottom, and that makes my visibility poor. Cold air rolls into the valley. The inversion that forms traps my pollutants, which is my smog, and fog, mist, and haze also forms, which makes visibility very poor. Urban climates, very quickly. The differences between city and rural areas. Firstly, in a city, I'm not going to go through this with you. You need to know why your city is hotter, because of the artificial surfaces that absorb heat, the taller buildings, the industries, the vehicles, etc., that generate heat. You need to know that. Urban heat island, warm city, we have like an island effect, 30 degrees, 32, 34, 36, an island of high temperatures surrounded by a rural area of lower temperatures. An island of high temperature surrounded by a rural area, almost like an ocean, of lower temperatures. Learners, a pollution dome and a heat island is not the same thing. They occur in the same area. The heat island refers specifically to that effect where I've got a hot city surrounded by a cooler rural area. I do not refer to pollution at all. The pollution dome also occurs over the city, but here we speak about the mass of polluted air that is trapped by the inversion layer and prevented to rise. The pollution dome occurs in the same area that the heat island occurs in. They occupy the same area, but they are two different entities. Calculate the difference. Calculation very simple, 33,3 minus 29,4. The term that describes the difference in temperature is my heat island. Very important before we go off. How does building density contribute to the CBD having higher temperatures? Now, be very careful. We get caught up in a question. The question is only asking for building density. It is not asking anything about the artificial generation of heat, etc. Only about the density of the building. So limit your answers to what is being asked. You are not going to speak there about vehicle engines generating heat or the artificial surfaces that absorb it. You're only going to speak about the density of the buildings, how close the buildings are to each other, the heat being trapped, etc., the heat being reflected between buildings, etc., not any other aspect of it. So learners, it looks as if we have come to the end of our session for today. We've come to the end of our session for today. I've really enjoyed it. This was my very, very first telematics broadcast, and I'm not sure if you noticed how nervous I was, but I hope that you have learned at least one or two new things from me today, and I hope that after the session you're going to go and sit with your books, that you will go through all your climatology, and that at the end of the year you will choose both question 1 and 2 in your exam where the climatology questions are asked. So once again, thank you very, very much for joining us this afternoon. We hope that you have a fruitful study session after this. And from me, Regan Ford, I wish to thank you very, very much for your time and for being very, very patient with me today. Thank you.